All right. So now we know all the steps we need to do to get a wave function. But how does that actually happen in practice? Can you guess what we're going to use to get there?
Math.
Math.
The secular
The secular equation. Yep, which is a lot of math. Okay. Now. Yeah. Now we have a way to construct our guess wave function. What was the symbol we gave our guess wave function?
Like an italicized phi, or is it just phi?
Just phi.
Okay.
The other one we're going to call lowercase phi.
Is that
Maybe.
Uppercase versus lowercase.
Yeah, I guess that one's technically not uppercase, but it's only 2 lines. Okay, and we have a way to construct the wave function, and what are we trying to do to it to get a good guess?
Minimize
minimize
energy.
Yep, we've got to minimize energy. We need, and we know we need, to find E naught or a low energy. But how do we do that? So we derived a couple of equations in the past. Got E is equal to, oops. All over integral of this guy. And then we have this linear combination of atomic orbitals that we just displayed. I'm going to switch the symbol to A sub I for the contribution, just because eventually we would get a bunch of C's everywhere and it would get really confusing. Okay, so we have these 2 expressions. Let's plug them into one another. Because we know this, we're trying to get these guys, and we know we got to get the energy small. So our energy just becomes integral of the summation in there. AI, and we're going to take the complex conjugate of this whole thing, H, and oops, actually this should be J. All over complex conjugate. Whew. Okay. We can simplify this a bit. What then can we pull out of this expression? What are the A's again?
Consonants.
Constant, so what can we do?
Pull them.
Yep. Pull them out of there.
Do we take H1 out or H hat out?
No. We can't take that one out because it's got to operate on the wave function. So we're stuck with that portion. Oops. Now we get this. In the past, we were using orthonormal wave functions, meaning if these two are not the same function, what happened to them? They were zero. If they were the same function, what happened to them? 1. However, these basis functions are not orthonormal. But now, our basis functions are no longer orthonormal, which sucks. Well, I guess it doesn't, because then we wouldn't exist, but I don't know. Okay.
Should there be an edit on top of that sigma?
Yeah, there should be. But rather than write these integrals out a bunch of times, we're going to develop a shortcut. And we'll talk about what these integrals mean in a minute. We'll reiterate it later for more chemically meaningful things in a bit. Rather write a ton. We're going to do this. We just shorten that to Hij, and we're going to call this guy the resonance integral. This one we're going to give the symbol Sij. This one is called the overlapping. This gives you an idea of the quality of overlap between your basis functions. This thing I really don't want to talk about right yet, but we will when we talk about rule theory. It'll make more sense when we get to rule theory. Okay. What do we got to do to that energy?
Minimize.
Got to minimize it. We still haven't done it. We still need to minimize. Energy. How do you know you're at a minimum using calculus?
Second derivative is
Did you think it was first derivative?
First
who's
derivative.
first?
Yep.
Yeah.
First derivative lets you know slope and lets you know if you have a slope of 0 you're at the minimum. We could be at the
Or
maximum.
max, right?
Right. You okay, Joe?
Yeah, so when your second derivative is positive.
Your second derivative about the point tells you a little bit.
Right, that's okay.
What are the only things we can actually modify in this equation? So these things, they're just atomic orbitals, right? They're just some function. We can select different ones, but after we've made our selection, can we change these things? No. What's the only things in here that we can change?
The constants.
We can only change those coefficients, we can only change those constants. So if we are trying to get the smallest thing here, what are we going to take differentials with respect to? The variables that can change, right? What are the ones that can change?
The constants, or the coefficients.
These coefficients. So, the only variables we can modify after we've selected our basis sets are coefficients AI and AJ. So we're trying to set that equal to 0. Okay, if we apply this, where we have partial of E with respect to A sub K, where it could be either I or J, is equal to 0. We get this equation. And itches.
Did we use this in playground?
We did. We
Okay.
wrote.
This-
We
I
all the,
remember this.
all the stuff I'm skipping from here to here took us like 2 to 3 classes, I think.
Yeah.
So like, what is going on for exams when it comes to this stuff?
More about the ideas, what are you doing here, and the application. So like, you'll have a Huckel theory calculation question that utilizes all of this stuff. Okay? Don't panic, you'll see, it's easy. Ish. It's easy.
Crazy.
Okay. So this set of equations, you have a handful of different ones for each coefficient you're looking at. This is known, this can be solved using a determinant. Which we'll talk about how to solve that in a little bit. H11 S11 H21 S21 H goes all the way to HN1 minus SN1 H12 minus S12 H1N minus SN N 2 S22 oops, H2 and all the way down scrambling down. This is known as the secular equation. It allows us to minimize our energy with respect to each of the coefficients. What this will do, this will result in n different values of E. Then we use each of those values of E, we plug in back here to solve for our coefficients, which we use to calculate each case of I.
So we're doing the determinants, so it's H11 minus EF11, right?
This is 1, 1.
It's your matrix or
Yeah.
stuff.
Matrix stuff.
N1 and N2. What is,
Yeah.
what is all that?
N is to whatever basis function we pick up to.
Okay.
Oh, it's just a.
Just trust it for now. We'll go to Hookel theory and it'll all be better. I promise. Okay. Other thing to recall. Our guess was constructed utilizing these coefficients. But we shall select or specify our optimal wave function using our selected basis set as J, 5J, excuse me, I, J, what are we doing on time?
We got
It's 11. Make a
Okay.
rush.
Yeah, 11. This is complicated. This is why we have computers to crunch this stuff for us. However, this was really known and developed, I believe, like 40s, 50s.
It might have been.
Might have been before that.
It might have been 30s, I think. Right? And
Yeah. Well, and then Hookel had to do it, so it had to have been even older than that.
Yeah, I think it was like 20s or 30s that root 10 came out
Yeah.
with those equations where you were putting
Yeah.
up in linear algebra.
And this is when they started utilizing, what was it called? Something analyzer. I can't remember what it was, but it was literally a machine to help people crunch numbers.
Oh, never mind. Root 10 was 1951.
I'll try and find it. But basically what had happened was there was an engineer at MIT that was very interested in building like one of the first computers, sort of a computer. It took a lot of people to operate. If I can find pictures of it, I'll send it to you. But honestly, that was very complicated, and it was easier to try and solve some of this stuff by hand when making different approximations. Computers started to trickle in and make things better, but we'll talk about one of the ways you can solve these things by hand. Okay, you erase the slide.